basically I will talk about QFT. QFT is supposed to be, so I'm not going to say anything about QFT in the first lecture, but eventually I want to talk about QFT. And QFT is supposed to be quantum field theory. Okay, so it's from physics, and we want to have some mathematical understanding of quantum field theory, because idea came from quantum field theory, like really influenced the various branches of mathematics in the last 20 or 30 years. Okay, and its influence kind of, usually physics was always kind of closely related with geometry. Okay, but now its influence seems to even to direct number theory, like that. So, interesting subject. So let me begin with a quoting Richard Feynman, one of eminent quantum field theorists who has invented something called Feynman path integral. Okay? And Feynman said the goal of physics is to produce numbers. Okay? It's completely natural here, because physics whatever theory, you want to predict something. That prediction you want to observe, okay, by doing some experiment, okay, and every observation it gives some numbers, okay. So the goal of physics is to produce number, okay. But you want to produce some meaningful number which tell something about your physical system, not just any arbitrary number here. So we want to produce numbers and meaningful numbers. Okay, what kind of number would physics produce? Okay, that is one of the goal, okay, of this program to understand. So let me turn to the math problems. So how we produce number in mathematics. Okay, if you think something in terms of geometry and algebraic topology and so on, how we produce number. Yeah. So I will talk about that for now. So let me pick R a commutative link. So this would be my ground link, okay? Or this could be like my ground field here. Then let's consider a Kuchain complex. So this is a Kuchain complex. Here, it's nothing but just increasing sequence of R modules, etc. Start somewhere, okay. And then there are this connecting homomorphism of R module, okay, increasing degree by 1, and d square equal to 0. Okay, this is a Kuchain complex. Okay, this I think everyone knows that here. So I'll begin with Kuchain complex. Okay. Now, if you consider Kuchain complex, of course we would be interested in the Kuchain map. So what would be the Kuchain map? So if I have two Kuchain under the same ground link, so we want to find certain map between natural notion of morphism. Is first it should be a module map. So F will send B to W, preserving here, and this B and W both are graded, so we want to preserve the degree. So this will be my notation for degree. So F would, for example, send element with degree I to element in degree Wi. So it's degree preserving map. That's an obvious statement. And then it should commute with differential. df. Okay, this d is there, and this d is there. Okay, and this is completely natural thing to do, because if I have something like that, and I have another wi, something like this here. Okay, then we have differential d here, and we have another differential D here. Then we have degree free-serving maps, so there's a map F here. There's another map F. Actually, I don't distinguish. So F actually means like composition. I mean, there are many components, okay? Sending I's component to I's component and so on. There will be map like that between two degree free-serving map here. Then if you look at each square, from here to there are obviously two ways to go. One is first apply D, send F. Another is first apply F and apply D. We end up same thing. And this condition for cochain map this module map is cochain map is nothing but that this diagram commute at each square. Okay. That's completely natural notion that everyone knows. I mean, I'm just saying doing the first class of homological algebra, okay? Thing here. So this cochain map. So cochain map commute with this map here. Okay. Now, so that is a cochain, and I defined what is cochain map. They're calling all this thing here. And one purpose of doing cochain complex is, of course, this notion of cohomology. So if I have a cochain complex, we can associate corresponding cohomology, which I'll be denoting by H. First, should I write them HB, etc. This is just the kernel of the modulo image of D. Okay, and because underlying chain is R module, then obviously corresponding cohomology is also R module because it's quotient by R module here. So this would be cohomology. So we have cohomology here. Now we can regard cohomology because cohomology, this is cohomology, cohomology group or cohomology module, and so on. We can regard cohomology itself as a cochain complex. No problem, because we can regard cohomology of B as a cochain complex with zero differential. Okay, because cohomology would have also grading, HI plus 1, and so on. Okay, then zero map is also modular map. Okay, and zero square is zero, so it's also cohomology. So you can regard cohomology as another cochain complex around here. Okay, so that is kind of trivial but important idea on here. Now, if I have a cochain complex, assume that I have a cochain map from W to B to W. This was cochain map. Then we know we have cohomology, and we also have a cohomology of this guy. Okay. Then obviously we can expect something. There may be some induced map which came from cochain complex. Okay. Let's denote that map by H of F. Okay. This map is some map which has been induced from cohomology. And why that is true? Because if you look at the definition of cochain map, it's clear that a cochain map sends a kernel of D to kernel of D. Right? Because for student, cochain map is satisfy FD equal DF, so it means that FD alpha equal to DF alpha, where alpha is in the source. Okay, this is true. So if alpha belonged to kernel, if alpha was kernel of D, the first one, then D alpha equals 0, so we get F0. Okay? But this is module maps, so it sends 0 to 0, so it must be 0, which is D alpha, F alpha. So if alpha is kernel of D, image of alpha is also kernel of D. That's okay. My same argument, say if something is image of D, then it will be sent to image of D. Okay? So cohomology was defined by the quotient, okay? But this cochain map naturally induces unambiguously map between the cohomologies. Okay? So you see, cochain complex was originally designed to deal with some cohomology theory. Then cochain map really works very fine here. So any questions so far? Okay. Now, let me introduce notion of a quasi-isomorphism. Okay, so in algebra, it's the following is the completely typical thing to do. So we introduce some algebraic structure. Okay, then you want to study those algebraic structure together with structure preserving map. So you have to study algebraic structure together with morphism. So if you study group, you have to study group homomorphism, etc. And linear algebra, okay, you have to study vector space with linear map, or like that. So that is natural. So we introduce notion of cochain complex, and then introduce morphism of cochain complex. Then we want to say when two cochain complex is isomorphic. Okay, that's a natural thing to do here. But here, interesting thing is the notion of isomorphism in the strict sense, such that we say F is isomorphic cochain map if F is an isomorphism of underlying module. Okay? That definition turns out to be completely stupid. Okay? Because of the following property, you know. If you think about cochain map, okay, this is some condition to be satisfied. Okay? For example, you can see the example come from like differential geometry. So when you learn differential form on a manifold, okay, then of course it form a cochain complex because exterior derivative square to 0. Now you consider map between two different manifolds, smooth map, and you can pull back the K form here to K form there. That pullback map is actually a cochain map, like cochain map and so on. Okay, so cochain map, making cochain map is not easy. You know, you have to invent something like here, because with this condition to be satisfied. But so you know, it is completely easy to just make any cochain map by following obvious construction. So we have some bi here and bi plus 1, bi minus 1, etc. And let's consider wi minus 1, wi plus 1. Let's make this guy here. Now let's consider a map S which is degree minus 1. Any map, any morphism, then you also have degree minus 1 map down here for each slot. Okay. Then we had the D here, and we had the D here. Okay, so this is the situation here. So if I start from BI, I can just go here and come down with this map. Okay? Then I'll obviously obtain a map from B to W. Or I can come down and go up to come here. Okay? Then I can also make map from B to W. So let S be any map from B to W such that degree of S is minus 1, shifting minus 1. And let's consider map H defined to be ds plus sd. Okay, ds plus sd. Okay, Then obviously this is a map from B to W, and the degree of H equal to 0. That part is obvious because degree S is -1 on here. Then let's compute the H minus HD. Okay, let's compute that. Then this equal to 0 because D square, so it's a 0. So this part will, if I do parsing, it will be D square S, D square equals 0. So it will just give us D as D. The second one, okay, if I put minus D as D plus SD square, okay, so this equals 0. Okay. So it is trivial to make a cochain map. Okay. Then this idea tells you that there's some homotopy around. There's some homotopy around here. So if both F and, we say F and F prime are homotophic, a cochain homotophic, we say cochain homotophic if F prime can be written as F plus SD plus DS. Well, yes, it's -1. Okay, degree can be always easily traced, so you don't need to mention. I will never mention that anyway. And you say SD plus DS is homotophic to 0. If you make this definition, you will easily check this is actually equivalence relation. Okay, so we're dealing with the equivalence clause. Okay, so the cochain map has equivalence relation down here. So okay, so there's a notion of homotopy. Right now then if you look up the example from algebraic topology, when you deal with the those homotopy saying, okay, so if you start from some topological saying to the some other, I mean, there are some if you consider morphism between topological spaces, okay, here, then you want to find the inverse morphism, etc. Then how you do that? Starting from here, you go other space and you come back. Then you want them to be identity, but there's a notion of homotopy. So you better say, if I come from here, come back, that composition is homotopic to identity. Okay. Then of course, if I start from here, then I come here, and I come back, then it's homotopic to identity in that space. Okay. So in the algebraic topology, strict notion of inverse does not work. Okay. Some composition of two things, both direction, is not identity, but it should be homotopic to identity map. Okay, because homotopy map. So that's why strict notion of isomorphism of cochain complex does not work. Okay, and we obviously know following thing: some cochain map, the difference homotopy would be vanished at the cohomology, right? Anything homotopy part, this part vanishes because on cohomology D vanishes. So D something vanishes on cohomology. So although we cannot say strict isomorphism on the chain level, but we can now say strict isomorphism on the cohomology. So that defines the notion of quasi-isomorphism. Quasi-isomorphism, or weak equivalence, sometimes in topology, in homotopy theory, quasi-isomorphism is a morphism of cochain, or you may simply cochain map, or morphism F, which induces an isomorphism on cohomology. Okay, that is definition of quasi-isomorphism here. So, in other words, if I map from B to W, okay, then dF must be same as ft, but then there's a cohomology of V, and there's a cohomology of W, then we learn that there's an induced map on cohomology, then we want HF isomorphism. Yes. Yes, please.
I understand that if the maps are homotopic, then they are quite homotopy implies quasi-isomorphism.
Yeah, it's an example. That is one example of quasi-isomorphism.
It's not equivalent. I wanted to. Any quasi-isomorphism comes.
If I have a quasi, if I have quasi, if F is quasi-isomorphism, any morphism which is homotopic to that quasi-isomorphism is also quasi-isomorphism.
But is it true that in some sense any quasi-isomorphism comes from?
No. 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 I think answer is no. No. So quasi-isomorphism is a cochain map which induced morphism map on cohomology is isomorphism. Okay? So this is definition of quasi-isomorphism. Yeah. Now we should be very careful about following saying, assume that I have a morphism, isomorphism between two, if both HB and HW is a module or vector space, okay? Then we can assume that we construct certain isomorphism between two spaces, okay? But that, in general, has absolutely no relation with quasi-isomorphism. Quasi-isomorphism is isomorphism which actually came from underlying cochain map. Now, you see, for physicists, up to homotopy, you can regard that as actually up to equation of motion. Like if you do the classical physics, okay, like you want to find the notion of observable as some function and the configuration space, etc., then you have to think that up to equation of motion. Okay? Because if something differs by equation of motion for classical observer, that would be exactly the same thing. Okay? We cannot distinguish. Because classical physics happen in the solution space of equation of motion. So think modular everything equation of motion. If two things are different, modular equation of motion, okay, classical physicists would say that is relevant. So that is kind of notion of homotopy around here. So you can say, and homotopy or homology, something like here. So this is something related to on-shell and off-shell of physics, etc.
Which is on-shell? The homology? Or
Homology, you can say homology is on-shell. Yeah.
the chain level is
Off-shell, yeah.
Okay.
So that is actually exact analogy. Here. Okay. And then, of course, the idea is that if two cochain complexes are quasi-isomorphic, then people regard them as equivalent. Same thing, like here. Okay, then problem, of course, will occur. I have no intention to lecture about homological algebra anymore, but the problem occurs that if you identify two cochain complexes by quasi-isomorphism, okay, you want them to be an isomorphism. Then you want to, of course, like find the inverse and here. But okay, quasi-isomorphism is not really isomorphism in strict sense. So quasi-isomorphism is actually not invertible. So almost you're never able to do this. I have VD, I want to find quasi-isomorphic cochain complex. Then you want to find a quasi-isomorphism. Then you want to find inverse. But this will never happen. Almost never happen, unfortunately. All you can do is that I have a B to W, then you kind of insert something in the middle. X1, Xn, then X1 is quasi-isomorphic to B, then it's quasi-isomorphic to B1, and you go like this there. You got Bn, something in the middle, like here. Okay, then eventually you show that B is quasi-isomorphic to W. Okay, so there's nearly no direct connection down there. So that's why you have to go to drive category to just invert quasi-isomorphism. Okay, but this all strange phenomena occur because we have to deal with something with homotopy. Okay, there's some homotopy instead of set theoretical one. Instead of set of element, we kind of have to consider some like homotopy type. So that causes all those problems here. So and let me give an example in this thing. So assume that M is a module, just R module. This is R module. Or K vector space. Or you can just regard it as vector space. Okay? So module, R module has no grading, ordinary vector space. I mean, I will confuse vector space and module all the time. Okay? I should not confuse that, but anyway, some R module around here, and there's a no degree. So then we simply regard, okay, degree is 0. Okay? Then we can regard this as just cochain complex. You put as many 0 you want in place. Then you say this is 0 map and this is 0 map and so on. Okay? Then you can regard just any R module as a cochain complex, which degree is concentrated at 0. Okay. Now, assume that you are able to find some cochain complex some D. Okay. Let's find some. Let's consider some cochain complex. So map F. So and all the other map is 0 map. Okay? Such that the cohomology of this cochain complex B is concentrated at degree 0. Okay? And is isomorphic to N. And so this cohomology all vanishes. Okay? So like that. Okay? Then this is exactly. Then we are constructing a quasi-isomorphic model of module. We construct a cochain complex, which is quasi-isomorphic to module. Okay? So then, because we regard R module as a cochain complex, because quasi-isomorphism is the sameness of cochain complex, okay, this R module and this cochain complex must be regarded as the same thing. Okay? And what is this? It's just nothing but a resolution of module. So this is resolution. Okay. Now you can imagine if you learn basic thing, if you go module or some, which is now print module, then we want to have, but perhaps this corresponds to projective resolution and so on. Some module, like then you do the resolution is not unique. Okay, you can have many different resolution here, but all those resolution is just they are all quasi-isomorphic to original R module. So that is an example of here. So that's why. Okay, so that's why study of quasi-isomorphism and homotopy category and drive category is essential to just even for simple commutative algebra business down here. Okay, so this picture, good, let's see. Now I still have to produce number, so I'll produce number from this picture. So now what you have to remember now is that any cochain map is defined of two homotopy. Okay, of two homotopy down here. Then obviously we want to produce something which is invariant on the homotopy, because even within the homotopy class, actual homotopy is involve choices. Okay, you choose representative of class. We have class here. We choose a representative of class to communicate with other class. Okay, and the result should not depend on our choice of representative. Okay, so if I have something with homotopy, we want to find homotopy invariant. Okay, but we want them to be number, for example. Okay, homotopy invariant doesn't need to be number, but want to be a number on here. Oh, no, here number means ground. Yeah, so now let me consider a cochain complex. Okay, but now I want to regard cochain complex. It's defined over ground field instead of number. Real number or complex number, okay? Some number. So complex over ground field K. And you get this real number. Yeah. Then we have corresponding homology of this guy. Okay? And then I consider ground field. Yeah. So this is cochain complex over K. I regard this as a cochain complex over K. K is an algebra, so it's a module of itself. Degree K concentrated 0. We have 0 map. So I can regard this also as a cochain complex. Okay. If I go to the cohomology, then I also disregard as a cochain complex. Okay. Then let's start to construct the map. So here I'm going to consider two maps. Map from H to cochain complex, and a map from cochain complex to number. Okay. Such that both F and C are cochain map. Okay. So here, because differential equal to 0, the condition for being cochain map is df equals 0, because no differential here. And here, because there's no differential here, the condition is CD equal to 0. Assume that I have such a map, okay, of certain degree, of course. And of course we have to say, because this is user map, I want to say degree of F equal to 0. Okay. This is degree preserving map, because taking cohomology preserve degree. But here we regard degree of K is ground field, so it kind of should regard as degree 0. So this map could be like various map actually. I'm not really talking about single map, but degree of C is non-zero. So let me say some minus n or something, whatever. Okay, degree C of non-zero map around here. Now how we construct this map? Okay. This is a standard thing to do. Assume that in most cases, like cohomology of this cochain complex is finite dimensional. Okay, so this is a finite dimensional vector space.
I'm a little bit lost now.
Yes.
Where did you start from here, and what are you constructing?
I said I want to find the homotopy invariant. We have cochain complex that is defined, cochain maps are defined of two homotophies. Right? So I want to find the homotopy invariant. Invariant which depends on homotopy type, in homotopy class only.
Of complexity?
Yeah. Homotopy class of cochain map of complexes, cochain complexes. Because so if mind of resolution which are kind of homotopic with each other, okay, then we do not want to distinguish them. So we need proper invariants for that.
Okay, so take complexes,
Yeah.
complexes,
Yeah.
produce something that is invariant
And to
to homotopy.
Homotopy, yeah. Because that is really something, we are always doing that actually. So I mean, after I explain this construction, then you immediately recognize what I'm doing here. Now, here construct a map. I want to construct a quasi-isomorphism. So here I demand F is a quasi-isomorphism. So why I want to have a quasi-isomorphism? Because I want to, my number that I'm producing would be actually come from composition of this thing. I go F and compose with C. Then from homology, directly I can get some number. Okay? If our search diagram. But I want, of course, something related to cochain complex, as she asked. So if I change that thing, something simple, but that should be quasi-isomorphic one, right? That's kind of obvious. And so this is, I want this quasi-isomorphism. So how I construct quasi-isomorphism? It's extremely easy here. For if I have a kernel of D, if I start from here instead of this, kernel of D, something annihilated by D, that element we just take homology class. Okay? And which is something is not kernel of D, you just send it to 0. Okay? In that way, you will produce a map from here to there. Okay? And conversely, because this is my finite dimensional vector space, my assumption, then I just choose a basis of this cohomology. Okay? And then find the representative of that cohomology class. So let E alpha be a basis of cohomology class. Okay? Then I want to then I want to find O alpha in B such that for each E alpha in the base, find O alpha in B such that D O alpha equals 0. So O alpha is, and cohomology class of O alpha is E alpha, because H is the cohomology class of here. So this is named for I find a representative of cohomology class. Here I would say O alpha is a representative of cohomology class, and then just define a linear map from H to B equal to O alpha and linear. Okay, so this is just a choosing representative of cohomology class linearly. Okay, if I do that, then cohomology class of O alpha is, of course, the class of this. Okay, this is E alpha by definition. Okay, so it means that because D alpha equals 0, we see that DF equals 0. So it is a cochain map. Okay. Now I'm just checking if that is induce an isomorphism on cohomology. It induces isomorphism on cohomology because the cohomology of H, 0 is H itself, because there's no differential. And the cohomology of BD is H by definition. Okay? So it induces actually not just isomorphism, it actually induces identity map on the cohomology. So this is a quasi-isomorphism. So choose a representative down here. Now, this choice, all those things is defined up to homotopy. So, you see, F is homotopy to some f prime, which written as f plus 0 ds. Yes. Okay. And this map C is homotopy to C prime, C plus S R D, whatever. Where S is a map from H to B, degree of S is -1, and R is a map from B to ground field, which degree is degree C -1. Okay. We know both of this map F and C, okay, are defined up to homotopy. Now, my claim, obvious claim, is that this map, composition CF, is homotopy invariant. So let's check that. C prime composition F. Composition is CF. I'm ignoring composition sign. CDS and RDF plus DRD square S. Okay, I just did the computation. And D square equals 0. Okay, and DF equals 0. And CD equals 0. Okay, so C prime composition F prime is C composition F. Okay, so we have just constructed homotopy invariant of this thing. Any question? So this is homotopy invariant in here. But now, although I did some funny thing, I mean, this is something we are really just doing all the time. For example, assume that we have differentiable manifold, then we have some cycles. Okay, I mean, so we have chains and differential forms. Okay, then we define the integration of differential form over chain. Okay, that gives a pairing, that gives a number. Okay, that gives a number. But that integration satisfies Stokes theorem. Okay, Stokes theorem, which always satisfies Stokes theorem. So C, I mean, I can even write down in this way: C d alpha equal to boundary of C alpha. This is K cochain and K chain. It satisfies Stokes theorem on here. So this Stokes theorem tells you following: if I fix my this space as a cocycle, okay, homology cocycle, my integral does not depends only on the cohomology class of the differential form. Okay, and if I choose closed differential form, an integratable cochain, that integration depends only on the homology class. Okay, of the chain. Okay, here that is the message of Stokes theorem. Okay, so here I'm really doing that. Here, although it looks strange because there's no chain or cochain, basically integration over some chain of, you regard this as differential form and this is the drum cohomology, and you regard this map by integration by some K chain. N chain in this case, okay? Then basically this composition, what is this composition? This, I'm really describing integration, okay? So if you consider a compact manifold of dimension n, oriented compact manifold of dimension n, then your fundamental class will give you a cochain map from drum complex to the ground field. and if you make a composition of between quasi-isomorphism from cohomology, round cohomology to the cochain complex, okay, then that's exactly what you are doing. So all those integration of fundamental class is just a representative, some way of construction of this kind of map. Okay. Now, in the dimension n case, like compact manifold, of course, H is bounded, start from H0 to, this is all bounded from below and above. So degree 0 to degree n. Okay. Then we also, in the compact case, H to n-dimensional homology is one-dimensional. Okay. And if this is compact, is non-degenerated. Okay. So this map, this actually map induce a pairing on H by this map. Because it's a cochain map, it also induce something. The pairing on H, and that pairing, in this example that I'm talking about, is nothing but the Poincare pairing, which gives you the Poincare duality. No, I mean, if C, okay, if C is non-degenerated, okay, that induce a pairing on H. No, general complex together combined with these two, not just the complex.
You have some extra structure.
Yeah, this is, I mean, both C is an actual structure. C.
Yeah, but you don't have product. How do you get product on it?
Okay, I'm sorry. Yeah, I mean,
I understand what you mean.
yeah, okay. So of course, in that case we have product. Actually, that would be my next topic. Yeah.
That's what you mean.
Yeah. Right. So this is kind of offshore way of doing that. Okay, I mean, kind of homotopy version of what we are usually doing in mathematics. So here. So that's why we have product. Oh, we have that's why all those theory of those integration theory and drum, etc., Poincare and Hodge, what they are doing is meaningful because actually we have homotopy invariant by the construction on here. Now, like, do I have like 10 minutes, right? Yeah. So in 10 minutes, I'll start to make big jump. So I want to say something about A-infinity algebra and L-infinity algebra. Or in general, just homotopy. Algebra. So as Weidong mentioned, we usually deal with cochain complex with differential and some product. Okay? So we can say it's space of differential form, exterior derivative, and match product. Down here. Then the product, okay, it could be like graded commutative and associative product. Okay? But important thing here is the differential is a derivation of product. Okay? Exterior derivative is graded derivation of extra product. Okay? So, if I have a cochain complex, and without if I have a graded algebra, okay, together with this condition, we may say compatibility condition, we call this DGA. DGA means differential graded algebra, or differential graded associative algebra. So this is nothing but graded associative algebra. And then without product, we have square zero. So we have cochain complex. And then together, this derivation of product. Such a structure would be called differential graded algebra. Okay? Or you can say DGA, you can regard, of course, graded algebra as differential graded algebra, of course, with zero differential. Or you can regard ordinary algebra as differential graded algebra with zero differential and degrees concentrate to zero. So we can really should regard DGA as just a generalization of algebra. Okay? So we are doing algebra class now. Here. Then, of course, we are introduce new algebraic structure. This is not new, but the class. If this structure here, then let's consider another DGA, the same ground ring or ground field. Here. So what would be the natural notion of morphism between two? First of all, without product, they are cochain complex. So it should be cochain map. So FD must be DF. It's a cochain map. Secondly, without differential, they are algebra. So you want them to be an algebra map. Okay. So what else? So this would be definition of morphism of DGA. Okay. And if algebra with unit, then of course it preserve unit. It should send 0 to 0 and all those things and linear, etc. But this would be morphism of DGA. Then here it's a question. Then we have actually problem. Question is following. Assume that F is a DGA map, DGA morphism. Okay, and that F prime is homotopic to F in the sense of cochain map. So F plus DS plus SD is F prime an algebra map. Okay, this is the first question we have to ask, right? Answer is no. It completely destroys the being property of algebra map. I mean, you can easily kind of see, algebra map satisfies this relation, but if I change F to this guy, no way it would be an algebra map. Okay? So it means that this notion of morphism of DJ is ill-defined in terms of homotopy. So in other words, but that notion of morphism we have seen here seems to be extremely natural. Okay, if you just consider the DJ itself, actually means that notion of DJ is ill-defined. DJ should be replaced with something which behave well with respect to homotopy.
Maybe you can adjust the morphism to make better definition of morphism. But you're saying that's already implied. You have to change the whole thing all at once.
Because morphism must be extremely natural.
Okay.
But you can cook up something. You make notion of very complicated notion of morphism. But you cannot explain why morphism should be. But if you just change DJ to something which well-defined by localization of homotopy, localized well up to homotopy, you have to replace DJ with something else. Okay? Because of homotopy. The result is you give up notion of DJ. DJ you regard as a special case of A-infinity algebra. So A-infinity algebra is just associative algebra up to homotopy.
Yeah, but I can just say, like, maybe you can just say, you replace your morphism. I mean, you keep the DEA, but you change the morphism.
Yeah, I mean, that just works,
Like a pair of F and 0 is the usual one, the one you start with. And then the one new one is called F prime and S. The pair, F prime and S. And then they satisfy this condition. Yeah. That would be your morphism.
Yeah.
Anyway.
I mean, it actually, that is also work. I mean, doing that thing and that thing is also same thing. Okay? But it will be like cumbersome. I mean, you know. So it turns out there's a natural generalization of notion of DGA to something called homotopy associative algebra, which special case is DJ. But here the point is why don't really kind of start to bring that up, the following point. The point is the important thing is not A-infinity algebra have some relations, okay? You don't have some complicated relation. The whole point is not replacing something simple like this to something complicated. The whole point is that we want to find better notion of morphism of DGA. I mean, we can actually stick to DGA, no problem. But you want to find a better notion of morphism. Because why? We want to find notion of morphism which behave well with respect to morphism. So instead of morphism of DGA, we'll have to consider morphism as an A-infinity morphism. Okay? Then A-infinity morphism actually would be, remember, F was a map from B to W. Okay? This map here. But now we'll have to actually consider a tensor product of Bn. And we'll consider this kind of map. Let's say this is Fn. Okay? And collect all of this thing together. Okay? This kind of thing will become A-infinity morphism. And of course, F1 is F here. So I'm not going to write it down, the relation. I mean, it's easy to explain if some more time, but I'm not going to do that now. Then we say, A-infinity morphism is quasi-isomorphism if F1, which is a cochain map, okay? F1 is F1. Cochain map is isomorphism, quasi-isomorphism of cochain complex. Okay? Then we regard two A-infinity algebra, or two DGA, if you want, which are quasi-isomorphic as an A-infinity algebra as the same thing. Okay? Simply because of homotopy. Now, another favorite algebra, besides from associative one, is of course Lie algebra. So let's consider natural notion of DGA. DGA. Here, this is just graded Lie bracket. Okay, so without D, this is just Lie algebra, grade Lie algebra. And D is just cochain complex. And we have same condition. D is derivation of bracket. Okay? Then we call that DGA. And of course, we have same problem. Okay, we have same problem. We define natural notion of DGA morphism as cochain map, which is also Lie algebra map. Okay, but we'll have the same problem of localization of this thing. So then DGA will become part of L-infinity algebra, and we say 2DGA is quasi-isomorphic equivalent, same. We can regard them as same if they are quasi-isomorphic as an L-infinity algebra. Oh, yeah. So all this notion, the construction could be complicated, but the idea is that because we have to deal with homotopy, okay, there's a homotopy around, every notion we have should be relaxed, okay, become much more, soft, okay, to deal with. Okay. So this is extremely natural thing to do down here. Okay. So this will end of my first talk. Yeah. Thank you very much.